Okay, so today I'm talking about nanotubes and electronics of small-scale structures. And I should say that I've tried to gear this talk toward undergraduates. So if you're an undergraduate in the lab, in the audience, please ask me questions as we go along if it doesn't make sense. And if you're a faculty, then you especially have to ask me questions because if it doesn't make sense and I've really done something wrong. Or if you want to know more about it, I can say a lot more than I'm showing here about anything. So I'm going to start by just giving a general background on mesoscopics research. I'm a condensed matter experimentalist, and I focus on small-scale structures. So I'll define what those are, talk about why it's interesting, and then talk about my specific research on carbon nanotubes, what the history of those are, why they're interesting, how we make those devices, and then go on even more specifically into some data that we've taken on these materials, looking specifically at low-dimensional behavior, one-dimensional behavior, and even we call zero-dimensional behavior of these objects. Oh, dear. OK, so that's, look at that. That's interesting. OK, so I just want to start by showing the people who actually do the work on this. Some of it I did a postdoc, but a lot of it is done by my current research group at University of Illinois, and a lot especially by my postdoc, and some students in collaboration with other groups at Michigan State and at Harvard. And of course, it's funded. We couldn't do any of it without funding from the NSF and the DOE. OK, so the basic, for all of the work that I do, we really ask one big question. What happens electronically when we shrink things down, right? If you take a piece of metal, a spoon, a faucet, and make it really, really small, down to the nanoscale even, billionths of a meter, how do electronic properties change, right? What's different about a very, very small object compared to a very, very large object in terms of the physical principles, right? How does the physics different when things are small versus when they're big? And you can think of this if you just first consider, a piece of gold that's, a few millimeters and you can hold in your hand, and that obeys Ohm's laws, right? You guys have seen this, V equals IR. You sort of know what goes on there, okay? Then, on the other hand, you take a single atom. And if you've had quantum mechanics, you sort of know what goes on there, too. It obeys quantum mechanics. So, particle wave duality, it can go through barriers without stopping. An elephant can't do that, but an atom can. It has phase coherence. It fills, the electrons fill atomic shells. So you sort of know what goes on either side of this, big things and very, very small things. And the question I ask is, what happens in between? What happens when you have something that's a few atoms long? Here's a nanotube that's about 10 atoms in diameter. Okay? That's small enough that you can still see quantum properties, but big enough that you can actually measure it. Right? You can't measure a single atom with probes, but something like this you can actually measure with probes. So this is the area called mesoscopics. It's something between macro and microscopic. It's small enough to see quantum properties, but big enough that you can still define a bulk property. You can still study it in the way that you do bigger things and think about what the physics there is. So what really interests me is how do you get from here to here, right? How do you build up your physical understanding? How do you go from quantum mechanics to big things? And what interesting science is there to learn along the way? So this mesoscopics research is what we call a bottom-up approach, starting from small things and making them bigger, a bottom-up approach to understanding physics and to making devices. At the end of the day, as electronics get smaller, it's more and more interesting to look at smaller devices, what happens in small structures. And I've written here just 3 big questions that you'll see keep coming up throughout this talk. What are the questions we ask when we make things small? Well, one is, how do low-dimensional systems, here I say one-dimensional or zero-dimensional systems, differ from 2 or 3 dimensions? Right? It turns out that, here's a picture of Alice in Wonderland as she found out things are different when you're smaller, right? You guys are, OK, anyway. So, in small systems in physics, you see stronger interactions among the particles. Electrons interact much more strongly. You can see interesting phenomena due to that. You get unusual correlated states to these strong interactions. You see quantum mechanical behavior. You do see different things when things are very small and confined to small spaces. We also want to see, can we see and study quantum properties, right? Well, how does quantum mechanics manifest itself? If it's not one atom, but not a big thing, if it's a few atoms across, how do you see quantum mechanics in these things? And also, can we make devices out of these? Can we make something novel in these really small structures and make something useful and interesting? So these are the basic questions that we ask in this research. Now, as I mentioned, there's a practical motivation, and that's to make really small circuits. Now, you guys have probably seen Moore's law before. Moore's law says that the number of transistors on a chip, the transistor density, on any given chip is increasing exponentially every year, right? So if the density is increasing exponentially, it means the size is decreasing, right? And this has seemed to work out amazingly since the 1970s, and the computer manufacturers are really desperate to stay on this curve, right? But as things get smaller, we're already at the size where the size of a transistor is the order of 65 billionths of a meter, across. That's really, really small. That's nanoscale already, right? I mean, you could think that's a couple hundred atoms across right now. So already, just practical considerations in electronics of the things that we use every day forces us to try to understand and work with nanoscale objects. And again, you can see that as you pattern things down, you can get to about 65 nanometers. You can use advanced technology to get a little bit smaller. But if you start moving to things like nanotubes, you can get even smaller if you work with these sort of structures. This sort of nanoscale mesoscopic research is also key to using quantum mechanics to make more advanced devices than you can make with classical mechanics. And one example of that is a quantum computer. Now, a quantum computer is something that uses quantum mechanics to get many more bits than you can get with classical mechanics. The idea here is that you use things like spin, which is a quantum property of things, of electrons, and these quantum mechanical states, say spin states, not only can be an up or a down, right? That's one bit, up or down, but they can be in a superposition of both up and down at the same time. So you don't only get two states out of that. You get, up, down, plus down, up. You get four states out of just 2 bits in that case for a quantum computer versus a classical computer. So that's just one example. So in general, for classical computers, you need 2 to the n calculations. From n bits, you can do 2 to the n calculations. And for a quantum computer, you only need n calculations. Okay, so you can get much more powerful parallel processing out of a quantum computer than out of a classical computer. But in order to do this, you have to use quantum mechanics in small structures. You need to manipulate spins. You need to define qubits. You need coherence in small structures. You need to harness the quantum mechanical power of small structures to implement these sort of quantum devices. Okay. And finally, you guys have heard of nanotechnology. Mesoscopics is smack in the middle of nanotechnology. It's researching on small-scale structures. In general, nanotechnology is just making and studying things on the nanometer length scale. That's basically what I'm talking about here. There's a lot of interest in this in all different areas of chemistry and physics and materials science, from putting colloids into paint to working on carbon nanotubes like I do. And there's also just been a lot of funding for this area. You can see that the investments in nanotechnology have been in the orders of 1.5 billion for the past few years. So there's funding and a lot of interest in working in this area. So this is the motivation for doing this sort of research. Now, I'm in physics. There's a lot of examples of nanotech research or mesoscopics research in physics. Here's just 3 to give you a sense of the work that I'm talking about. People can work on, I said mesoscopics is going from 1 atom to 10 atoms. And people do that explicitly by using a special probe to put individual atoms in a line and see how they can build up from 1 atom to lots of atoms and see when it starts getting properties of a wire versus of a single atom. They do this using a scanning tunneling microscope. People also can fabricate nanostructures. Here's an example of a nanostructure that's used as an optical trap that only lets through certain wavelengths of light, right? Used for understanding how you can trap certain wavelengths, also for all optical switches. Again, the scale of these holes here is sort of 100 nanometer holes. And, or you can study things like molecules, DNA, molecular transistors, nanotubes. These are just different examples of this sort of research. Now, my research focuses on carbon nanotubes, and you can consider these sort of a highlight of this area of mesoscopics or nanotechnology. Carbon nanotubes are tubes made of carbon. Now, carbon is important. It's a building block of life, right? Everyone knows carbon is important. It's also, if you think of the different forms of carbon, they're all really cool, right? You can just take carbon in this form, and you get diamond, one of the hardest structures around. You take sheets of carbon, and you get graphite. These days, you can take a single sheet called graphene and isolate it and study the really 2D properties. We do some of that as well. You can also take the sheet of graphite and roll it up, and you make a tube. This is a nanotube. If you look at it, it just looks like soot, but it's a really cool crystal property. It's a perfect crystal here. And if you look at it, if you measure it, it sort of looks and acts like a really narrow wire. Okay? And this was discovered in 1991 by a group. A guy was just looking at different, he was looking for buckyballs. I don't have those on there. He was looking at different forms of carbon. He took a graphite source and a welding arc. You know how you do welding? You make a spark and it gives a lot of heat. Have anyone seen this? Just a welding spark. And he had like some iron around, and he just sparked the graphite with the iron around, got a lot of soot that looked like that, put it under a microscope, and lo and behold, there were nanotubes, and there was a Nobel Prize. Okay, so okay, it's not quite as easy as that. And he actually was looking for something. That's basically how these were discovered by this group, and they turned out to be really amazing materials. As I mentioned, they're just sheets of graphite that have been rolled up into a tube. They can be rolled up different ways. And as I'll show, they form naturally. You can just grow them in an oven. They roll up really small, diameters as small as a nanometer, a billionth of a meter in diameter naturally, right? So really 1D systems, so narrow that they're quantized in that direction. So one-dimensional. They can be really long, millimeters, even centimeters, right? Imagine something that's a billionth of a meter in diameter and a centimeter long, right? These have been done, right? People can make these. So you can use these to, arrange them in 2D circuits. You can look at them as 1D wires. You can cut them up into small sections and make them act as particles in a box or as zero-dimensional systems. They're very flexible in terms of looking at different physics. You can roll them up into single wall, one time into a single tube, multiple times to multiple tubes, into ropes of nanotubes. All of those are interesting for different reasons. The way that you roll them determines whether they're metallic or semiconducting. It just turns out that if you sort of roll it across like this, it's metallic. If you roll it with some funny angle, it can be semiconducting. So you can get both semiconducting and metallic behavior out of them. You can see almost perfect conduction. They're very strong. They're lightweight. They carry a lot of current. They conduct a lot of heat. There's lots of possible applications of these. The reason you're probably not seeing them so much in every application is that they're so small and they just sort of grow in an oven a little haphazardly that you can't really control all these properties very well. So it's hard to control their properties. It's hard to manipulate them. You grow them, you see what you get, you hope it's good most of the time. So that's the biggest, and you can't put them where you want them. So that's the biggest limiting factor so far in applications of these. But they're still, they're still very good to study, and people are applying them for some things, as I'll mention. Okay, so what are some of the applications? People have been looking at these as small wires for electronics, as chemical sensors. They have a pretty big surface area. There are even companies out there that are selling these to detect dangerous gases. They work pretty well. Nanotweezers, you can take little tiny particles between your nanotubes. As super strong materials, as quantum computers. There's a lot of basic physics, as I mentioned. Probably my favorite application is the nanotube elevator to the moon. Has anyone seen this before? No? Yeah. It's actually a company. I encourage you to go to liftport.com. They're trying to make this. Now, when I first started showing this slide, I don't know, 5 years ago or something, they had a launch date of, 2012 or something, and now it's up to like 2054. So I think every year the launch date's moving 10 or 20 years, right? But it's still pretty cool. The idea here is that nanotubes are extremely strong because they're made of carbon. They have that nice crystal structure. But because they're hollow, they're pretty lightweight. So you can make a long cable out of these that goes into space. And then if you're trying to supply something in outer space, like a space station, you just use a little electric ratchet that slowly inches its way up the nanotube, up this cable. And therefore, it avoids having to blast off and work against gravity, right? It just sort of adiabatically inches its way up, and you save yourself on rocket fuel. You can really cheaply supply things in space. And it only works with the nanotube because any other cable would collapse under its own weight. It wouldn't be, to make it strong enough to go up to space, it would have to be really thick, and then it would collapse. But nanotubes are both strong and lightweight. So it's sort of a clever idea that utilizes a relatively new material for an application that just couldn't have been done before. So I think it's pretty neat. It may not work. It's still pretty neat. Apparently, they're also worried, if you go to their website, they're worried that if it gets cut by like space debris and it falls, it could knock the Earth out of orbit. So anyway, but it's neat regardless. You should look at it. Okay, so that's what nanotubes are interesting for a variety of things. Let me tell you now how they're made. I told you how the first person made them with just an arc laser with a spark and a graphite source. In general, to make tubes, you grow them. You just need a heat source, a carbon source, and a catalyst. The catalyst is usually a heavy metal like iron. So they've been made by using lasers or arc evaporation. The most common way now, I think, is using chemical vapor deposition, where you just you put your catalyst, typically iron particles, on a surface, and then put that on a chip, on a little chip like this. You put that chip in an oven, use your recipe, heat it up to something like 900 degrees, flow a carbon source through, and the nanotubes then grow off the catalysts and the carbon, from that carbon source as a reaction. Okay, so you put an oven to 900 degrees, reduce the iron to nanoparticles, flow carbon, and the nanotubes grow. Okay, so it's kind of like cooking, just a recipe that someone developed, and it's amazing. It just sort of works. So here's the oven. It's a tabletop experiment. Here's the gas handling system. We flow through methane and hydrogen and argon. Here's the inside of the oven. These are the heating elements. There's a little silicon chip. This dimension, that chip is about 0.5 centimeter, to give you a sense of size. Little things to think of. We put it on a little quartz boat. At one point, I thought, oh, well, why are we buying quartz? Let me put it on a glass slide. Anyone know what's happened to glass slides at 900 degrees? Well, it's funny, because their melting temperature is actually, should actually be a lot higher. It's just that they have a lot of defects in them, so it wasn't a pretty sight. Anyway, so we put our little quartz boat, and there's our chip. After we've grown the tubes, we just take that chip out, image it, and you can see here's the catalyst, and these little things, the nanotubes growing off the surface. Right? It's actually pretty amazing. They just sort of grow. And with the right recipe, that's all you get on the surface. Notice a totally clean surface with catalyst and nanotubes. Okay, so how do we see them? As I mentioned, you should find it remarkable that we can even see this. I told you they're 1 nanometer in diameter. You can't use a normal microscope. That's way smaller than the wavelength of light. Right? You can't just image these things. How do we actually see these on a surface? Well, you need specialized technology like atomic force microscopes or scanning electron microscopes to see them. Has anyone used atomic force microscope? It's not faculty? No. Yeah, these are, so it's actually pretty cool to see something that's that small. And to do it, you have to sort of remotely sense it. You don't see it, but you use something else to sense it and then reconstruct the image. So what we typically use is called an atomic force microscope. It's a very sharp tip. And at the bottom of that tip is just a few atoms. It's just there's a few atoms at the bottom of everything. At the bottom of your fingers, a few atoms poking out. So it's a few atoms poking out. You bring this tip very close to a surface, okay? And there's a very slight force of attraction between the atoms at the bottom of the tip and that surface, just a van der Waals attraction there. And the tip is on a cantilever, and that cantilever is pulled a little bit down to the surface. And the amount it's pulled down is determined by the height of the thing on the surface. Okay, so as you scan that tip around, it's pulled more or pulled less, and you can see how high the thing is on the surface by how much this tip is pulled. And you can measure how much a tip is pulled by just bouncing a laser off of it and doing an interferometry experiment to see exactly how much that tip is pulled in nanometer scale. Right? And then you reconstruct that scanned image, and you get something like this, where you can see basically what I'm looking at is the height difference of 1 nanometer off the surface, and I can see where these nanotubes are. Okay. You can also do something like this with a scanning electron microscope. In that case, you bounce electrons off a surface, see where they reconstruct that image, and then use that to image things that are extremely small, because electrons have a really small wavelength. So you need something like scanning electron microscope, atomic force microscopes, and you can actually see things this small. And this is also why nanotechnology is sort of a recent phenomenon. This sort of technology didn't exist on a common, easily accessible scale until recently. We then need to contact them, right? That's not so easy. Again, you have something that's nanometers in diameter. It's only a few micrometers long. How do you put your probes on it to measure the conductance? What I really want to do is take one of these, a fluke, a multimeter, and just put the probes in the nanotube and measure it, right? But you can't do that. So how do I make contacts that are big enough that I can put the probes on it? And here we use what's called lithography. And that's just a process of using sort of a photosensitive, it's like photography. Use a photosensitive material, put a mask on it. You use light, which has very small wavelength, right? So you can make a really small gap based on your light. Okay, so you radiate it, you expose a little area, you develop it, that little area gets exposed, you backfill it with metal, then you lift off the photosensitive material, you're left with a little tiny patch of your metal in a really small area that you've designed. Okay, and you can see here, this metal, here's our metal that we patterned on the surface using this process. This length scale is 5 micrometers about, and here you can see a nanotube with the contacts on it. Okay, so if you use optical lithography using light, you get about 1 micron feature sizes. With electron beams to expose, you get things down to 10 nanometers. We use electron beam lithography a lot. to contact these things on such a small scale. It's actually a very laborious process. Okay? You can see here, here's what the devices end up looking like. Here's our nanotubes. We contact these, and then we go out to something that's bigger, and here is something that's a millimeter in diameter, in length, and we can actually just contact this pretty easily. Okay? So it's amazing that we can actually measure conductance on things that small just by scaling up to bigger sizes. And this process might take 10 days of work or something, actually, just doing all the different steps. At the end of the day, you can measure something that's really tiny, which is neat. Now, some of this has been done, just making the tube devices are things that people did before I started researching. So, if you want to research, you have to do something new. So one of the things that I've been working a lot on is making more different sorts of contacts and gates and getting local control of these nanostructures. And so I spent a lot of my postdoc time and time at Illinois trying to take nanotubes that are contacted and put more gates on them. And this is tricky because usually they're so small that they get damaged when you put things on them or near them. So we developed ways to put a small insulating layer over the tube and then align more local gates, we call it, for sort of local probes and local control. Here's gates on top of the tubes. Here's the tube here, and these are gates next to the tube. And this is where we have gates underneath the tube. And we put an insulator between the tube and the gates so we can have layer by layer control of the barrier. So if we put a very thin insulator, we can have something that's pretty well conducting to the tube, maybe a tunnel contact. If we put a very thick barrier, we have a gate where it's just electrostat capacitively coupled. Other things that we've done is use an atomic force microscope tip to actually bend the nanotube. Again, you literally take this tip, drag it across the nanotube, and make it bend. And here's some bends we've made in nanotubes themselves. And I'll show later that this changes the conductance of the tube. We can measure that. Okay, and then sometimes we line these top gates over the bends, right? Combine everything we can do to make something new. So here's nanotubes where we've actually put the gates over where the bend is and away from it. Here's a double bent tube with 2 gates over there. So we work a lot to make things that are a little bit different, to try to use these local probes to get some local control over the nanotube properties. And we also generally measure at low temperatures. And we're interested in quantum properties. You don't see quantum properties at room temperature because at high temperatures, all you see are temperature effects. Right? Those are much higher energy scale than quantum effects. So we have to cool things down to near 0 degrees Kelvin, just near 0 degrees in general, any scale, to get the quantum properties. We use specialized refrigerators and cryostats to get these things down to very low temperatures. Okay, and again, the things we're looking at are, what happens when we have small dimensions? Can we see and study quantum properties? And can we make novel ultra-small devices? Okay, so here's a nanotube device. These are very simple measurements in a sense, right? The real difficulty is in making these things and getting the fabrication and making something new. Then I tend to do pretty simple measurements. Alternatively, you could have a very simple device and make very hard measurements. You probably don't want to have a hard device and a hard measurement because you'll never get anything done. So I've chosen to take a simple measurement, right? So what we do is we take our nanotube, treat our nanotube as a resistor, put a voltage across it, measure the current. 2-terminal device, very simple. A little bit more complicated sometimes. Here's our nanotube, have 2 contacts at the end, put a voltage across it, measure the current. Sometimes we have a capacitively coupled gate that can also affect it. Okay, and so you'll see things a function of what I call the gate voltage. That's just this, it tunes some of the energies in the nanotube as well. Here's a false color image. The back gate is usually just a doped wafer that we place it on. There's an oxide layer to insulate it. And then here's a nanotube in false color red and 2 contacts. A standard device. And again, sometimes we put other gates on it too. This is the standard measurement though. And what do we see if we just measure a simple nanotube? Let's just, forget gates, forget anything. Let's just measure this device, Put it, measure this with a back gate, end-to-end conductance. What do we see? It turns out even that is pretty interesting, right? So here's the conductance of the nanotube, or the current related to conductance, versus this back gate, this capacitively coupled gate. And if you just follow this room temperature, I don't have the temperatures, this is a room temperature line, the red, you see that it's 0, 0, 0 conductance, and then it turns on. And then you go back, and it's high conductance, and then it turns off. It's a MOSFET, right? That's a transistor. With a voltage, you can turn it on and off. So even a simple nanotube device with just a gate voltage is an ultra-small transistor. And people have worked to make these even better and found that they have better switching ratios than even silicon. Okay. Now, they haven't replaced silicon because they're just hard to get to where you want them right now. But in terms of physical properties, they're really amazing, even as just this simple sort of this simple sort of thing. So already, just in the very simple nanotube device, it's just a novel, ultra small thing. And you can see here, this is room temperature. You get much better properties in the blue and the green as you go to lower temperatures. This is 4 Kelvin. Now you might notice something else here. There's some wiggles on this. Okay, you think, well, okay, your data went bad all of a sudden, right? I went to even lower temperature, and now the data is even worse than it was before. It turns out these wiggles aren't bad data. There's something even more interesting that happens in these things. So, here's higher temperature, and then I think this is 70 Kelvin. As you go to 4 Kelvin, you see something else. It turns out this is Fabry-Perot interference. You guys heard of Fabry-Perot cavities? Some of you have, right? So the Fabry-Perot cavity is common in optics, right? It's just typically in optics you can put 2 mirrors at either side, and you can put a photon in there, and it can resonate back and forth between the 2 mirrors. You can see interference between the waves. Okay? Turns out the same thing happens with electrons in a nanotube. In a nanotube, you get nearly perfect conduction. They call it ballistic conduction. It doesn't hit anything along the way, right? Because it's this perfect crystal, right? The electrons are just going around the outside of this perfect carbon crystal, so it just goes from one end to the other without hitting anything, without losing any of its properties, of any of its phase. So it turns out an electron can go into a nanotube and bounce back and forth, and because an electron is also a wave, and because these things are so small that you can see quantum properties, the forward and backward paths of the electron can interfere with each other. You get a standing wave pattern inside the nanotube, right? But it's an electronic standing wave, not a photon. It's an electron standing wave inside this thing. And those are those wiggles that we're seeing. And you can see it, if you look at it a little bit differently, this is a 2D conductance plot where the black is low conductance, the white is high conductance, and we're looking as a function of this back gate and our end-to-end bias. And it turns out we see these oscillations because the electron wave numbers are changing as we shift the energy with the source drain bias, and as we shift the wave number with the back gate. And so we're shifting the phase of this electron wave as a function of source drain and back gate. And you can see this interference pattern. If you can you see sort of a pattern there? You don't believe me? Pattern? Yeah. It's not beautiful because it's a nanotube and an electron. It's not a photon in a cavity. But I guarantee it's a pattern that's been shown really beautifully by other people. This is not as beautiful data we've taken, but it's clearly an interference pattern that you can see here, which I found pretty neat. I was pretty excited to see that because it's 1D behavior, right? It's back and forth interference, and it's quantum, fundamentally quantum, and a thing that we're just probing with our wires. Okay, so let's make more devices. What happens now if we bend a tube and just put a gate over it? So here we have a nanotube. We've put one of these local gates on top, and we've bent the tube. So we have gates over where it's bent and gates over not where it's bent. Here it turns out we can see preferential conductance through the bend. So we can choose a tube in some regime where it's not very well conducting outside from the bend. So if we measure conductance as we put voltages on the green and the blue probes, we see very little conductance. It's 0, but it's basically flat. Not much happens. And then we see what happens as we put conductance, as we put a voltage on this gate, measure conductance as a voltage on this gate near the bend, and we see a very, very strong response. Okay, so by putting a bend on the tube and putting a gate near the bend, we can locally tune conductance. It's like the bend makes a constriction, and then that gate opens and closes the constriction. So you can really, you can locally control your MOSFET type behavior. And there's physics behind this too. It turns out that when you bend a nanotube, you think of that crystal structure, you're making a local defect in that structure. So this is called a 5-7 defect. Just add up the number of carbon atoms there. And it turns out this sort of defect is associated with p-n junctions in the tube. This has been well studied before, but it's sort of neat to see that this sort of p-n junction, it's like a diode, and it can be tuned with a gate voltage. Right? So now you can really study what's happening on the very physical level and what's happening in terms of what you can measure in these systems. Okay, what else? So now let's measure a voltage on a local gate at lower temperatures with no bends. We have a nanotube that's contacted and a gate over it. And we're going to see what happens to the conductance of the tube as we put a voltage on this gate. We're measuring at pretty low temperatures now. It's not in the Fabry-Perot regime, okay, higher temperature than that, but just conductance as we move this gate. And actually, it surprised me. The first time we did this, we saw these wiggles. Now, these weren't Fabry-Perot wiggles because they're not just continuous oscillations. We saw what looked more like steps. A step, and a step, and a step, and a step, and a step. And we studied this a lot and found that we always saw about 4 steps. And the separation between the steps was a unit of E squared over H, right? This is just a fundamental unit, right? It's not like a number 1.2 or something like that. It's a number that might be associated with some fundamental properties of the system. And it turns out, as I show you, it is associated with a fundamental property of 1D systems. So we saw what looked like these quantized conductance steps. And it's hard to see they look like steps here. You can look at it in a different way. This is a conductance plot. It's just high conductance is yellow and red, low conductance is black. And I just show you it to show that there really is a pattern of these steps. Right, you can see here that it sort of fits a pattern that you might expect here. And it turns out that these quantized conductance steps are actually expected in one-dimensional systems. It turns out that you can look at an equation for the current, and the energy dependence of the current drops out, and you expect quantized conductance steps in a one-dimensional system. So this is really one-dimensional physics that we're seeing here. It's because nanotubes are so small that they're quantized around the circumference, and yet you can get conductance through the length. And so only one, what you call quantum mode, one quantum mode, one wavelength, if you will, one wavelength of electron at a time gets through the nanotube, right? So first you have something that has an energy, just a wave like that. And then at a much higher energy, you get another wave coming through. So these are the different electronic modes, one at a time, that go through the nanotube. And they're spaced by some known energy. That's the mode spacing. Okay. So it's really, really one-dimensional behavior. It's been predicted, but it wasn't really seen before in these systems. And this happens because our gate is just locally depleting carriers in the tube, creating a constriction that's allowing these modes through as we increase the gate voltage. And these things were interesting. It's pretty exciting to see it. They've been seen in some other systems, never before in a really 1D system. And they can be used to focus electrons. They have some spin dependence to them that you can study, to look at the degeneracy of the system, to study interactions. There's lots of things you can do to study with it. So we're still looking at this, trying to understand it. And one thing we're still really trying to understand is why we see spacing of just E squared on H. It should have 4 E squared on H spacing, but we see 1 E squared on H spacing, which looks like we're losing some of the degeneracy in our system. And we're not quite sure what's going on there, but it makes it really interesting to study. But in general, like I said, it's just, it's really purely 1D quantum phenomenon in this system. Okay, so here's the last example I'm going to go into of research that we've been doing on these systems. And that's that nanotubes. I've been talking about sort of 1D behavior in nanotubes. Now I'm going to move into what happens when you look at them as zero-dimensional systems. By 0D, I mean particles in a box. Okay, so from quantum mechanics, you know that if you confine particles to a small enough space, a box, right, they start obeying quantum mechanics. You get quantized energy levels there. And so if you consider a short section of a nanotube, the diameter is so small, even if it's sort of long enough to contact, it's still a pretty small box, right? The effective area is really tiny. So if you have sort of if you have weakly coupled source and drain leads, the nanotube itself acts like a box, and the electrons are the particles in this box. We also call these quantum dots, or artificial atoms, as I'll show. So now the nanotube itself acts like a quantum dot, where our gate is just a capacity coupled gate that can tune the energy levels of this dot. You can think of it here, you get these quantized energy levels, right? And if your energy level is between the energy of the source and drain leads, you can get electrons going on and off your dot, your particle in a box. If your energy level is not between the source and drain leads, you get no conduction at all. So you get single electron conduction through this quantum dot, right? And you can see the energy level spacing is just particle in a box spacing because, and it's pretty big in this case. Okay, so if you look at conduction in this system, depending on where this energy level is tuned by the gate voltage. Depending on where this energy level is, you either get conduction of single electrons or no conduction. So you can see here, you get conduction showing a single electron is going onto your dot, then no conduction, then conduction again from a single electron. It's single electron transport. Right? You can think of it as a single electron transistor, or you can think of it as a way to approach single charge and spin control as well. So this in itself is it's sort of a cool system. People sometimes call these artificial atoms because adding single electrons, these energy levels, is like adding single electrons to the shells of an atom, right? So filling these energy levels is like filling atomic shells, and so it's in a solid state way of looking at at atomic physics or at chemistry, physical chemistry. So this is well known. This quantum dot behavior has been known for 20 years now, but it hadn't been studied that much in nanotubes, and it was really hard to control this sort of behavior in tubes. It turns out that nanotubes make really good quantum dots. They're so small that you can see this quantized behavior at relatively high temperatures, higher than in other systems. They're pretty clean. You can make these just using standard lithography. And here are some examples of this single electron transport peaks, right? Each of these peaks is associated with a single electron coming on and off the nanotube. Okay, so before we started working on this, most people who made quantum dots in nanotubes just used the source and drain leads to define the dots. We wanted to make something more controllable, so we thought, why don't we use our local gates to define these dots in the nanotubes? The idea here is we put two gates on a tube. We deplete carriers beneath these gates, right? So there's no electrons here, no electrons here, and then the dot is going to be defined right between these two gates. So it's a very controllable way of making a confined region of electrons in nanotubes, a quantum dot. And you can see it here. Here's a long nanotube. Contacted off here, right? And then we have one gate defining one lead, another gate defining another lead, and then we put a local one in the middle just to tune the energy levels of that gate. As you can see, when we do that, we got a really nice controllable quantum dot here, right? These peaks, right? So we put this barrier at some potential, this barrier at some potential, tuned this middle gate, we call it the plunger, and we see that we get single electron conductance in a very, very controlled way in these nanotube devices. Okay, so why is this good? Well, it's good because if you can make one, you can make more. Right? So we're not, we can show that we can make one quantum dot in a nanotube. Why not make two or three? This is a scalable technique. So here you can see you can make a double quantum dot. Again, you have a source and a drain, right? And then you use gates to define two weakly coupled regions of electrons. And if a single quantum dot is an artificial atom, then a double quantum dot is an artificial molecule, right? You can control interactions, atomic interactions between this molecule. Look at bonding and anti-bonding states, all those things you might have heard from chemistry, you can actually look at and study now. Okay? And in this case, you only get conduction when the energy levels of both of these quantum dots line up. So if they both line up, you get conduction. If one of them doesn't line up between the source and the drain energies, you get no conduction at all. Okay. And so we've made these double quantum dots. We can make them in a couple ways. One is just, like I said, using lots of gates. You can see that here. These gates define each dot. The blue ones define the dots. The yellow ones tune the energies of each dot. We've also made it by just having a dot that having a nanotube that had a defect in it and tuning that defect. Right, so here's a defect and multiple gates, and gave us independent control of the different regions of the dot. So what do you expect if you're measuring conductance? Well, if you have two dots defined by two gates, right? Dots defined by different gates, say gates 1 and 2, tuning the energy levels of the dots. Okay, so these gates 1 and gate 2 are tuning the energy levels of dot 1 and dot 2. You only get conduction when the energy levels of both dots line up. Okay, and they both line up only at certain points, like here and here and here and here. And actually, the black points and the circle and the white points are bonding and anti-bonding states. Right, so you get conduction when at these certain points when the energy levels line up, and nothing in between, and then these numbers tell you how many electrons are in any given state as these energy levels line up. This is what you theoretically expect. When we measured our double dot system, this is what we saw, this honeycomb pattern pretty much as predicted. And this is really exciting for us because it showed us we had really complete gate control over a double quantum dot system in a nanotube. So now we can really study all these different bonding states. So again, here you can see we get conduction, these conduction peaks, these bright spots when the energy levels lined up, nothing when the energy levels didn't line up. Okay? We could do further studies of these, look very carefully at the vertices. There's all sorts of predictions as to what you're supposed to see, what these energies mean. We extracted things like the capacitance of the nanotubes to each other and to the gates and the interaction energies. These numbers don't mean much. I'm not putting him here to go through it all, but just to show you that once you could have this level of control, you can really start extracting information from these systems and studying them in more detail. Okay. And there's an application. As I mentioned at the beginning, there are things like quantum computers, right, that we're interested in. That's why one of the motivations for measuring these mesoscopic systems. And there's even a prediction for making a quantum computer out of a nanotube, right? And the idea is this, is that you have this orange thing is the nanotube, okay, and then these yellow lines define quantum dots, okay, and then 3 quantum dots form a qubit where you have spins. These arrows represent spins, and the different spin states interact. and do computations. And this is a quantum computer made on a nanotube. And it's nice because it's sort of a linear, scalable computer. And if you can get one to work, maybe you can get many to work, and you can do all the calculations just along in this really nanoscale system. And as you notice, this idea of this schematic for a quantum computer looks pretty similar to the actual devices that we've been making. Okay, so we're actually getting closer to be able to do these sort of computations. And in fact, there's a recent paper that the group that I came from, the postdoc, has actually been able to do some interactions between qubits in this sort of system already on a nanotube. Okay, so that's it. I hope I've given you a sense of what this sort of mesoscopics research is, of what sort of devices you can make, and why it's interesting. As I mentioned before, there are three questions that we're continually asking. You know, how are small dimensions different? And the answer is that they're very different. Electronic properties are really different on the small scale. You can see things like coherent transport, Fabry-Perot I showed you. You can see transport of single electrons. You can see quantized conductance in 1D, things you would never really see in the macro scale, but are really fundamental and interesting and maybe even relevant to devices on the nanoscale. You know, can we see and study quantum properties? Yes, of course. In fact, quantum properties dominate at these scales. All of these things are really quantum mechanical. Right? Quantum mechanical events where we're seeing electrons as both waves and particles. We're seeing interference between electron waves. We're seeing energy quantization. These things are crucial at these small scales. And can we make novel ultra-small devices? And again, yes. You know, the simplest nanotube is a field effect transistor. We can see single electron transistors. We can build up to things like quantum computers. Right? We can do a bottom-up approach to making these devices and try pretty hard to use new technologies to configure systems to make even more advanced devices. And in general, I think that nanotubes are really model systems for studying these things, very versatile and fun to work with and think about. So thanks again. I'll end with a picture of the people who actually do the work, not me, them. And let me know if you have any questions. Thanks. Yes?
You have mentioned the quantum confinement of the electrons.
Yes.
Any change in electron properties. I just wonder, since for photons in such a small structure, there will be quantum confinement of photons as well.
Phonons? Yes. Yes.
And photons can interact with electrons.
Yes.
I just wonder, do you see whether there will be a large effect of the confinement of photons on the electron properties, or don't think there would be?
Yeah, that's a great question. It turns out that because of the structure of nanotubes, phonons are relatively weak at low temperatures, and so the phonon energy scales, you know, where you see just thermally affecting, thermal phonons is typically, I don't know, above 100 millivolts, and I don't know how, but I don't want to convert that to temperature, but much higher. We're typically working at the sub-millivolt scale, so maybe 100 times higher energy range is where you expect to see any influence of phonons. Now, there might be phonons at lower temperatures, but those are expected to be quantized at any regime where we're actually looking at electronics with a nanotube. So it turns out that electron-phonon interactions at these temperature scales are pretty weak, which is a big advantage for these quantum systems, right? So you're not losing energy or coherence or any of these things to phonon interactions. Yeah. Now, one thing that people have done in tubes, which I find really interesting, they've suspended nanotubes over trenches and actually looked at the quantization, looked at quantum fluctuations of the nanotube, just vibrational modes of a nanotube. And they've actually seen some influence of phonons in that case because they're actually just moving the lattice a little bit, but it's not as relevant in electronics. Yeah. Yeah.
Well, it seems that recently research on graphene is very hot.
Yes.
Any papers about graphene can be published.
Yes.
How do you compare graphene research with nanotube research?
Yeah.
Why is graphene so hot?
Yeah. So I don't know, for those of you who don't know about graphene, so I mentioned that carbon can be formed into sheets, and those sheets are usually stacked as graphite. And someone recently discovered how to make just a single layer of graphite. And that was thought not to be able to be physically possible because a 2D film should be unstable. It was thought to just wrinkle or just have fluctuations that made it effectively 3D. And yet someone is able to stabilize it with this highly advanced technology using Scotch tape. Right? So you take a piece of graphite and you put a piece of Scotch tape on it and you pull off the top, and these things cleave very easily because they're layered. And you take that, your tape now has a freshly cleaved layer, and you stick it on your substrate and you peel it off again, and you look at it very carefully and you find graphene, single layers. Right? So that was discovered about 4 years ago, and there's been an explosion in papers. I went to this big physics meeting, and I would say, this is almost every physicist in my field was there in condensed matter, and probably 10% of the talks were on graphene. That means like 1 in 10 condensed matter physicists is working on graphene. Okay, I don't know if that's a real number. That was my feeling there. So one question is, why is graphene so hot? It's new. That's a really big thing, right? I mean, in physics, you're always looking for something new. So if you don't have a new technique, a new material is a really good thing. So one of the things you see is that graphene's really easy to make. Anyone can make it, and it's new. So if you have a technique or have anything you're working on, you just put in graphene. Right? So we've done that too. We were looking at superconductivity in nanotubes, and now we're just looking at superconductivity in nanotubes and in graphene. Okay, so that's one of the things. It's really easy to substitute it in. So, and if you've worked on things like nanotubes, the fabrication techniques are very similar, right? If you've worked on any sort of mesoscopic structure. So that's, again, as you say, it's a new material. Lots of things may publish. It's sort of a steamroller effect where the more people publish, the more people are willing to publish, the more people are just doing anything on it. So, it's unclear how long that will last. But graphene does have some interesting properties. It's gate tunable metal in some sense, right? It's a semi-metal that you can tune with a gate, and so it may be applicable to making, a transistor substitute. If you can make if you can pattern sheets of graphene, it's all gate tunable, so you can really make transistors in an easier way than you can with nanotubes. You really have to place in certain locations. So that's one big motivation for looking at it in terms of electronics. It turns out that its electronic structure, the Hamiltonians that describe the electronics in graphene are identical to those that describe photons, right? So it's a way of looking at like photon physics in the solid state. So it has a Dirac equation that is similar to the Dirac equation for high energy physics. So people are thinking of all sorts of high energy experiments that can be tested in graphene. So one thing is it can tunnel through barriers that are much thicker than you'd otherwise see tunneling through, and that's been actually tested. Klein tunneling, I'm not sure what it is, but that's been actually shown recently. It has an anomalous quantum Hall effect. It has some things that you don't see in other systems. So, there's interesting physics there. I would say it's not necessarily more interesting than nanotubes, but nanotubes are now, 15, 20 years old, right? So it's new. Does that sort of answer? So I don't know. So my feeling on graphene is that it's an easily obtainable material that you can publish in, that you might as well do, and that has probably 5% of the current papers are really interesting and new, but that's a pretty good fraction. Yeah.
For the small electronics with the carbon nanotubes,
yes.
They perform a lot better at low temperatures. So for that, would that mean to build a quantum computer, you'd have to keep it at a low temperature?
That's right. Yeah, that's an excellent question. So the quantum properties show up at low temperatures. So the answer is yes. In general, to build a quantum computer for using these sort of materials, you'd have to do it at relatively low temperatures. Now, nanotubes have an advantage compared to other systems, is that, as you know, quantum properties show up more if you're smaller, right? So atoms show quantum properties at room temperature, right? So nanotubes are so small that you can actually see a lot of these quantum effects at, say, 80 Kelvin. So you can use liquid nitrogen to cool them down as opposed to liquid helium. So they might be cheaper to operate than other systems that really require helium or specialized fridges. So it's possible you still have to cool it, but maybe not as much as you would other systems that are bigger to use. But yeah, I mean, you'd have to cool it down, and then there's all sorts of, there's still, in any solid state system you want to make a quantum computer with, you always worry about external influences that kill your quantum properties or kill your coherent properties. This can be noise, it can be thermal effects, this can be connections to other things. That's just a huge issue in the field. So yeah, I don't suspect you'll see a quantum computer in the next 20 years, right, is my feeling, but maybe later, I don't know. Yeah.
With that low temperature effects and how that makes it more beneficial
That's a great question. The answer is, I think for things like quantum computers, it's an interesting thing. There's no really killer applications yet for these things. And I suspect if they made one, they'd find out how to do it. But everyone says, oh, you can solve algorithms, right? Well, I don't know. I don't see it's not like the economy is now down the tubes. We haven't solved enough algorithms, right? Probably quite the opposite. We solved way too many algorithms, right? and it's been a big problem. So I think that the applications will likely be, more for quantum computers and that sort of thing would be more Earth-based computer science applications, probably very specialized, traveling salesman-like problems, which are big deals for a lot of companies, but those sort of things. Space does have low temperatures, but it'd be very different unless we're actually going to make a base or something. You don't gain. It's so expensive to go to space. I think you might as well just use liquid helium here on Earth. Yeah, I think. Yeah. Also, it's funny. I don't know if you followed any of the space research. People have thought of putting things in space where it's cold and they can operate cheaply. The problem is that if you're near, if you're operating in space and you need someone to handle it, it has to be near a rocket ship of some sort, right? And those things are hot and dirty, right? So you actually want something to operate in space very, very far from your ship. The closer you are to the ship where you can actually handle it, the more you're getting fuel emissions and radiative heat and other things like that. So it's actually a little bit of a catch to think about operating in space. Unless you can leave it on a base alone and have it transmit, you're not really gaining that much. But yeah.
Some health concerns with this kind of materials. They said that they might act similar to asbestos to issue. How do you deal with that?
Right. So do you mean how do we deal with it in the lab, or how does one deal with it in general? Yeah, it's a great question. Yeah, it's interesting. This is, as scientists, I guess, as scientists, it's always a challenge to sort of push the best science you can as fast as you can and get the interesting results and still be a responsible human being in terms of what is the ultimate effect of your research, what is the ultimate effect of the materials that you're creating, what are the other things that are happening here. In this case, there's been some work on the studies of the hazards of nanomaterials. There's no known. I've looked at some of these studies, and to me, it's hard to tell what the real effect is. But for sure, things like nanotubes are shaped like asbestos rods. Do you think you don't want to breathe these things in? In my lab, we deal with extremely small quantities. If you saw the chips that we deal with, they're sort of half-centimeter chips with. We actually want to contact these. They might have 10 nanotubes on them. So, I tell my students not to put their noses in the oven after they've grown, but usually these things are pumped out at the other end. They have gas throwing through. So as long as I feel like they're not breathing in the oven and they're just dealing with small quantities, it's probably okay. There are companies that make barrelfuls of these, and I'm not quite sure what they do. I've heard, there's conflicting evidence. On one hand, people are using things like nanotubes to directly target cancer cells, right? They're injecting it into animals, and these things tend to go to the cancer cells, and they seem to be helping. On the other hand, they inject it into the gills of fish, and they get clogged up, and the fish can't breathe anymore. I mean, we don't have gills, that won't happen, I don't think, right? But it's not a great sign. So it's really mixed right now, and I guess the most we can do is be sort of be aware of this and try to be careful. In terms of breathing in and handling it, wash your hands, that sort of thing, and yeah. But
I got a question.
yeah.
So, the sizes of these nanotubes, right? Are they controlled by chemistry when you're making them?
Yeah.
Or so can you control the size of the diameter?
Yeah, that's a fantastic question, and the answer is yes. So nanotubes are a great field in that chemists and material scientists and physicists work together on these. So chemists are the ones who really discovered this and who've been working on the side of controlling their diameters. So yes, there are certain recipes, growth recipes, that tend to make smaller or larger diameter tubes. There are growth recipes that tend to make longer or shorter tubes, or that make multi-wall versus single-wall tubes. Even some recipes that tend to make more metallic or more semiconducting tubes. And so people are really hard at work on doing these sort of things. And they're somewhat successful. So I would say if you use a recipe that tends to make large diameter tubes, maybe you'll get 50% large diameter tubes, which is much better than you usually would, but it's not quite enough for industrial applications, right? You'd still have to have another process of centrifuging or something to separate these things out. But the answer is yes. It's a huge project in itself to control these things. And I've had students in my lab try to do it, and I feel bad. So every time a student comes to work for me and they do nanotubes, they say, well, why don't I just fix the recipe and do this or that? And I say, that's a research project in itself. I want you to measure them, not just make them. Right? So you sort of need to work very closely with people who make them. And
so why are they around? I guess what's the driving force for them? I mean, I don't know.
How do you roll them up?
yeah, I don't know what the driving force is, but I mean, energetically, it's a stable configuration, I guess. So let's. So I mean, you have to have. I mean, obviously, you have to match a carbon atom, or you can't just connect it any which way. But when they're actually rolled up, it's a stable. It's a crystal, right? So there's some. Let's see. There's some.
So they have to roll practically. You can't have a sheet.
They don't. Let's see. They don't. I see what you're saying. They don't start as sheets. They start as, where do I have a growth here? They don't start as sheets. So when you grow nanotubes, you're not actually starting from graphene. They're growing. So I think they start with the way they grow. And there's still some controversy as to how these things grow. But when they grow, basically these catalysts like iron, carbon is somewhat soluble in these catalysts. Okay, so at these temperatures, around 900 degrees, is when you break down your carbon source, like methane in this case. And methane starts cracking. I think it cracks at like 980 or 950. So usually you run between 890 and 950 here. So you start to crack the methane. You get some free carbon. The carbon precipitates onto this iron preferentially. And these iron nanoparticles, you have to use nanoparticles, right? So these iron particles are of the order of few nanometers. And the carbon forms on either side and starts growing as a tube. So it grows as a tube on the iron.
So does that shape then determine the shape of the nanotube? Like can the size of the nanoparticles determine the size of the nanotube?
I've not been able to determine. It does to some extent. It does to some extent, yes. It does to some extent, but not fully, because usually these nanoparticles are actually quite a bit bigger than the tube. So the tube is typically smaller than these. So yes, that's one of the things people have made bigger nanoparticles and grown bigger tubes, or smaller ones and grown smaller tubes. There's a minimum diameter of the tubes because at some point you get bending energy. So, it must be, it's probably 10, I mean, where's the nanotube picture? So I mean, at some point you bend, you can't bend it enough that you actually form a defect, right? So it's probably, 0.8 nanometers or something is the minimum diameter of it. And like I said, the particles are usually bigger than that. So they don't fully set the size of it, but they do, sort of wet, and they probably, depending on, something about the temperature and the energy of the bonding, right? They just form and grow as tubes. It's hard to know. I mean, for a while, there's a huge controversy for years as to whether the catalyst stayed where it was and the tubes grew above it, or whether it grew underneath. And now people think that, the catalyst stays at the top and it just continuously grows there. It's actually, people didn't know this for a long time. So, it's still somewhat of an unknown process and not entirely, but yeah, so. But yeah, if you could grow graphene in an oven like this, you'd have 1 billion papers right now. It's not so easy to do. People don't usually grow it, so they exfoliate it from graphite. So you just buy graphite and Scotch tape and we put it on silicon. Put it on silicon oxide. Actually, and so the other thing about graphene is that the real key to finding single layers was not just exfoliating it. Probably that's been done. But it turns out that when you look at it under a microscope and you have a 300 nanometer silicon oxide layer under the graphene, you can actually see a difference between 1 and 2 layers and more, right? So if you don't have that, it's just some interference effect. If you don't have that oxide layer, you just see lots and lots of pieces of stuff, and you'd have to do an AFM on all of them to see the thickness, and it's impossible. It's too time-consuming, too many things. But if you can actually optically see the graphene candidates, then you can actually find it and manipulate it. And that was the big difference there, which is sort of funny. But yeah, usually it's on oxide. You can only see it on these silicon oxide things. So